Hello, and welcome back to the alphabet of astronomy. Today is brought to you by the letter Y, and Y is for Y-Dwarf. If you've been around here for a while, hi, appreciate you, then the OBAFGKM spectral classification for stars will sound familiar. Sometimes stars on the low mass end are called dwarfs. For example, our sun is called a G-dwarf. M-dwarfs are the smallest spectral classification. Of stars, at least. Wait, spectral classes for non-stars? Yes! Recall that the definition of being a star is an object that is able to fuse hydrogen in its core. There exists an entire class of objects that are actually not massive enough to achieve this hydrogen fusing, but not small enough to be considered planets, and we call these brown dwarfs. And brown dwarfs have their own spectral classes. Well, actually, there is some overlap between stars and brown dwarfs in the ML classes, but in general. So beyond OBAFGKM, we have LTY, and this makes Y-dwarfs the coldest class of brown dwarfs. So for stars, the spectral classification is arranged by both mass and temperature. That is, O stars are the most massive and the hottest, and M stars are the least massive and the coldest. It's a little different for brown dwarfs. Because brown dwarfs aren't stars, that is, they're not producing this energy via the fusing of hydrogen, they actually cool down over time. So at the same mass, an older brown dwarf will be cooler than a young brown dwarf. Young brown dwarfs are hotter not only because of the heat left over from their formation, which takes time to dissipate, but also because they are doing some fusion sometimes. No, they're not fusing hydrogen, otherwise they'd be stars, but they can fuse deuterium, which is a heavy isotope of hydrogen, or lithium, which can generate heat for some amount of time until they run out of fuel. So for brown dwarfs, the LTY spectral classes are arranged by temperature, but not necessarily by mass. So what makes something a Y-dwarf? So this is the class of brown dwarfs that's almost a bridge between brown dwarfs and planets. The dividing line between the two categories is not always clear. A good rule of thumb is about 13 Jupiter masses, above which something is brown dwarf mass and below which it is planetary mass. This is based on the ability to fuse deuterium, but there's a lot of variables at play. But as I said, temperature is what determines the spectral class of a brown dwarf. So for Y-dwarfs, that temperature is between 200 and 500 Kelvin. Now it can be easy to lose context when we're talking about Kelvin and stars and 5,000 Kelvin, 6,000 Kelvin, 500 Kelvin. So just keep in mind that the human body temperature is roughly 300 Kelvin and 200 Kelvin is well below freezing. So the hotter brown dwarfs, these L and T dwarfs, were discovered and characterized back in the 1990s, and Y-dwarfs were only theoretical. This paper from 2003 tries to predict what the spectral signature of these, at the time, unnamed brown dwarfs would actually look like. Because these objects are so cold, their spectra are really dominated by molecular signatures, molecules that couldn't survive in hotter atmospheres, things like water and methane and ammonia. Y-dwarfs are also cool enough that they need to contend with the formation of clouds in their atmosphere. And then these theoretically predicted brown dwarfs were actually finally uncovered and observed for the first time in 2011. Yes, this is an entire class of substellar objects that we saw for the first time just 10 years ago. Astronomy is far from complete. We actually still only know of about 20 to 30 of these ultra cool brown dwarfs. As predicted, some of the spectral signatures of Y-dwarfs are very deep absorption bands in water and methane. However, the ammonia absorption lines actually turned out to be basically kind of covered up by some of these other absorptions. So although they were predicted theoretically, not really seen observationally. Also, there's a peak in the J-band that gets narrower as temperature goes down, so these very narrow J-band peaks are very typical of Y-dwarfs. So you can kind of see how we transition from things being late T-dwarfs to being early Y-dwarfs. And in fact, the spectral standard for the Y0 class of brown dwarfs is an object called WISE 17382732. WISE is NASA's Wide Field Infrared Survey Explorer, a mission launched back in 2009 that has been responsible for most of the discoveries of Y-dwarfs because they shine primarily in the infrared. So this is part of the spectra from the Discovery paper back in 2011. So in red, we see the spectrum of an object that's considered the spectral standard for the T9 class. So we're seeing the transition from T-dwarf to Y-dwarf in the green. Y17382732 has an effective temperature of only 350 Kelvin and is not even the coldest Y-dwarf that we know of. That honor goes to this guy, which has an effective temperature of only 225 Kelvin. So cold. I mentioned that narrow J-band peak before. Well, you can compare the J-band to the H-band to get a J minus H color, and this color actually can indicate the transition between T and Y-dwarfs as well. We see here this kind of transition as they start to get redder again as you go into Y-dwarf territory. So how common are these Y-dwarfs? Well, you may recall that smaller stars are more common, much more common than more massive stars. One might expect this trend to continue for brown dwarfs. After all, they form the same way that stars do, they just don't quite reach the same mass that you need to burn that hydrogen. In fact, this does not seem to be the case. Now, because brown dwarfs are so dim and cool, it's very difficult to detect them, Y-dwarfs especially. And so if you were just going off a pure number count, brown dwarfs would be very underrepresented. This is also an issue for M-dwarfs, which are the most common type of star in the galaxy, and yet we cannot see a single one by eye from Earth. Of course, scientists try to account for this detection bias, but it can be difficult, especially when you only have a few handful of these objects discovered. But it does appear to be true that in general, brown dwarfs are much less common than M stars or red dwarfs. However, it's still unsettled if there's a trend in occurrence rate across the LTY spectral classes. That is, are L dwarfs more or less common than Y dwarfs, or the same? This table from a recent 2021 conference summarizes the recent findings about the slope of the substellar initial mass function. So the slope being negative would mean that Y dwarfs are less common than L dwarfs, the slope being 0 would mean they're all equally common, and a positive slope indicates that Y dwarfs are actually more common than L dwarfs. I'd say the jury's still out on this question. So there you have it. Y-dwarfs are the coldest class of brown dwarfs, a class of objects that exist between hydrogen-burning stars and inert planets. Y-dwarfs are difficult to detect. We first did it only back in 2011. We don't know yet just how common these objects are, but I'd say they're not only ultra cool, but they're also pretty damn cool indeed. That was cheesy. Thank you so much for watching, and I hope you will come back and finish us off with the letter Z. Thank you. Have a good one. Bye.